This video shows how high-log discovery lets users manipulate large datasets in context using advanced visualization and generic data manipulation techniques. This video assumes knowledge of the high-log discovery framework introduced in other videos of the same series. Graphical user interfaces have brought tremendous new possibilities in many application domains: computer-aided design, drawing programs, network analysis, computer games. All those applications pretty much exhaust the capabilities of today's interactive computers, much to the benefit of their users. However, most of nowadays business applications, such as accounting software, customer relationship management, and even web search results and online catalogs, still take only a minor advantage of the capabilities of modern GUIs. These applications rely on forms, lists or table presentations quite exclusively, such as the CRM software. Indeed, a simple character-based terminal should be sufficient to use most of these applications. GUIs bring additional comfort and aesthetics, but no significant enabling power to manage the information presented. This is because the data being presented has no intrinsic visual representation that would allow taking advantage of our visual perception and our ability to manipulate graphic objects. Yet, there is a need to help manage the ever-increasing amounts of business data available online. More and more, business users of this data is shifting from simple data entry and selection tasks to complex activities, monitoring, analyzing and reporting on vast amounts of information, or taking informed decisions based on the overall structure of the data rather than on the individual values held in the database. Information visualization, as a research domain, brings some answers to help users make sense of large amounts of data. For instance, the high-log discovery application and software component lets you analyze and manipulate large datasets in a visual and intuitive way. It features a full set of tools to import data from various sources, create rich and expressive views, filter the data, annotate it, edit it, and create live or static reports. Through various examples, this video introduces new tools to edit rich datasets in context and the possible uses of these features. Based on high-log discovery's rendering model, we have created a streamlined interaction model that allows full editing of large datasets using a direct manipulation paradigm. This interaction model involves three steps: adjusting the view parameters, selecting the objects of interest, and perform one of the 5 editing operations on those objects: edit a value, add or remove attributes, add or remove data objects. Let's look at the first example. One of the first useful operations on dataset analysis is data cleansing. In this example, we see a 2D plot showing the distribution of mileage per gallon versus white for a population of cars. Some of those points show a 0 mileage per gallon value. These are obviously missing values in a dataset. To allow proper analysis of the trends and outliers in this distribution, we should either get rid of those points or set those missing values to some plausible values that will not mask the overall trends. To do so, Discovery offers standard graphic tools similar to the move and resize manipulators found in drawing packages. Here, one can select and move the points in a 2D plot. The subtlety here is that the coordinates of the graphic objects in the views are determined by the data visualized and by the parameters of the projection of this data onto a graphic representation. Allowing these operations while maintaining the meaning of this 2D plot implies that the data values are modified to conform the graphic changes performed by the user. In this case, we move the zero-valued MPJ objects to some other values that somehow fits the relationship that has been identified between my MPJ and white. Note that the editing operations on this view are inferred from standard graphical operations and the current view settings. Changing the layout parameters to show, say, a histogram of values, the interactors relied on those view settings. Because in this case the width dimension is not tied to a data attribute, the interactor won't allow resizing objects horizontally. Let's consider another application domain, defect reports management. Discovery allows displaying items as a tree map. Here, we see a tree map of the currently open bug reports for a software product. These defects are grouped by priority. The grid shows in a glance how are those reports distributed: 183 in low priority, 126 middle, 29 high priority reports, 2 critical reports, and 7 unassigned reports. Besides the count, each individual report is still visible as a small colored square. The darker the square, the older the report. Hovering the cursor on a square provides additional details on this report. A right click brings a pop-up menu that allows editing the report in a dedicated form, or moving the bug reports from a category to another. Using this grid as a starting point, the job of handling bug priority assignments benefits from more context to help manage the task. For instance, I can decide there are already too many high priority reports and decide to lower some of them before setting a new critical priority one. Or I can pinpoint an old high priority report, examine it, and decide either to lower its priority or to send a notification to the person in charge of solving the issue. The same interaction technique can be used in other views, such as this view that displays reports by person in charge. This view lets the team leader balance the workload of his team among the developers and assign both priorities and the person in charge of solving the issue. Of course, the views are synchronized so that it is possible to use both views complementarily. So far, we've seen how graphic interaction techniques could be used to edit data values directly and in context. Other useful editing operations can take advantage of dense and flexible graphic representations, creating and deleting data objects, adding and removing data attributes. We show how this feature can be used with another example application. Decision tables are sets of rules that follow the same structure. If the applicant is a single male between 25 and 35 from California, then his insurance premium is $250. If the applicant is a married female between 35 and 50 from California, then her insurance premium is $200. To show the structure of the rule set better, those are usually presented as a data table whose columns present the variable data attributes. Even with this representation, the number of rows, and hence the space requirements to show the full table, increases exponentially with the number of columns. Presenting this table as a tree map enables the space requirements to increase only as the square root of the number of lines in the table. Using a tree map also allows reordering the hierarchy of the table attributes to select precise subsets easily. Other rendering attributes can be used, for instance, mapping the color value to the insurance premium value. This allows one to understand the cost structure and possibly spot some errors, here the 2 black spots in New York and Virginia. While those two values could be edited using a graphical interactor, here we simply select those values and enter a new value for the premium in a text editor as an alternative to editing the view parameters. Now, suppose we would like to add a state to this decision table. Using this view, we simply select all the items within a state and choose the duplicate action. The duplicated objects are selected, and we can simply use the same technique as before to set their state to a new value or enter that state in a new text field. Next, we can edit the particularities for that state, for instance, unifying the values for male and female below 25 by using the delete action and editing the gender value to match both genders. Using similar techniques, one can add or remove data attributes for selected subsets of interest. This means that any kind of tabular or hierarchical data set can be created or modified using a simple and uniform set of interaction techniques. How is this implemented? All views in our application are designed using a unifying visualization model called linear state data flows. These data flows describe how data objects are mapped onto a graphical representation through a sequence of operators that are parameterized by the data object's values. Our data flow defines only 4 operators: partition, sort, assign graphic primitive to data objects or group of objects, assign decorations to the graphic primitives. Those operators are applied to the input data set either selectively or recursively. Iterators and local variables augment the data flow with state handling capabilities. Translating graphic actions into semantic operations is quite the same problem as drawing appropriate scales in a 2D space. It consists in inverting the sequence of transfer operations whenever it is possible. When the only operator is a graphic primitive assignment, as in a 2D plot, parameters that include one column of the data model are directly invertible, while parameters that are constants cannot be inverted. Here, x and y are invertible, while width and height are not. When the parameter includes a reference to an iterator, then the sort operator determines the successive values this iterator will take. If the data is sorted by a column, that column can be used for inversion. In this example, objects are drawn next to each other, following the order defined by the manufacturer column. Each X position can therefore be assigned to one of the manufacturers in a dataset. Finally, the partition operators are used to define the range over which the values should be mapped. Because the projection defines a reverse mapping between the display space and the data space, other graphical operations can be assigned a meaning in the data space. For instance, it becomes possible to specify complex queries in the data space by delimiting geometric regions. Let's select this banana-shaped region that describes the cars that more or less fit a correlation between mileage per gallon and weight. This area defines the left-hand side of a rule if the cars region is America and the pair weight MPG is inside the polygon, and a complex definition, then we could decide to do any sort of operation. This sort of rule is commonplace in some applications such as alarm filtering, but often the verbal representation is quite a challenge to understand. Allowing users to define those rules graphically allows the specification and maintenance of far more refined rules than could be possible using an interactive method. In conclusion, we have shown a new editing paradigm for large datasets that can be applied to a variety of contexts. This interaction model involves 3 steps: adjust the view parameters, select and mark the objects of interest, and perform one of the 5 editing operations on the selected objects: edit a value, add or remove attributes, add or remove data objects. This editing paradigm provides a better awareness of the context of the operations that needs to be performed. You can obtain more information on iLog Discovery at www.ilog.com/preview/discovery with a capital D and download the free preview version there. Other videos in this collection cover various other aspects of iLog Discovery, such as what is visual data analysis, the iLog Discovery rendering engine, various business applications of iLog Discovery. Thank you for your attention.